In this brief lecture, we will look at a certain elementary feature of the energetics of corrosion, which will give us a guideline on whether a material will get corroded. So in the previous lecture, we alluded to the reason why electrochemistry is hidden in a typical uniform generalized corrosion cell. The reason is that in a typical electrochemical cell, the anode and cathode are physically separated via an electrolyte. As opposed to that, here in a corrosion cell, the anodic region and the cathodic regions are short circuited. They are shorted. Okay, so if you have, let's say, two leads of an voltmeter, it is not possible to stick the leads of a voltmeter into this region and this region and measure a bias, potential bias. That's not possible. Okay, so that kind of a measurement is possible all the time in an electrochemical cell, but here that is not possible. So if you try to measure the potential difference between these two regions, okay, there will be no bias. And as we discussed in the previous lecture, the propensity of a particular region of the metal electrolyte interface to act as an anode or a cathode might fluctuate. What was an anode can become a cathode, and the other way around. So this is the fundamental contradiction. With no anode and cathode separated, with both the anodic and cathodic part being shorted, what questions can be answered? So what we aim to do here is that we want to look at a pair of reactions. So here we show an anodic reaction, metal getting oxidized, and a cathodic reaction, proton hydronium ion reacting with electrons to form water and hydrogen. We would take a pair of reaction and look at its delta G and ask whether this pair is spontaneous. The logic behind this is we have done this in many of the pairs of reaction that has gone into the design of batteries or fuel cells. So we take a pair of reactions, we imagine the anodic and cathodic reaction occurring at two different electrodes. We can look at the delta G, and if the delta G is negative, we say that the reaction is spontaneous. So along similar lines, we ask this question even in corrosion too. So how do you visualize this? So even though in the same interface there are anodic and cathodic regions, the reaction that is occurring in the anodic part is different from that in the cathodic part. So we imagine this system in terms of this physical system. So let's say you have a metal that is getting corroded. This reaction is occurring. So this metal is part of this working electrode. Okay, so this is where oxidation is taking place. So in this system, this is the cathodic reaction. Let's imagine the same metal, or chemically and structurally, physically, the same metal is in this region. So that is the counter electrode. However, in the counter electrode, instead of oxidation, this reduction reaction is occurring in the counter electrode. The rest of notations are the same, what we have seen in previous lectures. This refers to reference electrode. It is utilized for measuring the potential of this half cell. This is the counter electrode. So once you have this kind of a system, you can have an voltmeter which helps you measure the voltage bias, and you can have an ammeter which helps you look at the current that is transferred between the two electrodes. So in what way this system is similar, in what way it is dissimilar? So it is dissimilar in the following sense. In this case, when you have a corrosion cell, there is no potential bias between the anodic region and the cathodic region, okay, which can be measured via an voltmeter. As opposed to that scenario, in this case, you can measure the voltage bias between this electrode and this electrode. So in that way, this system is dissimilar from this system. However, in terms of the reactions that are occurring, these two systems are similar. In the anodic region, this reaction is occurring. Here too, this reaction is occurring in this electrode. In the cathodic parts, this reaction is occurring, and the same reaction occurs in this region. So this is the way to visualize and operationally implement this pair of reaction using this kind of a system. So the pair of reaction, for this pair of reaction, if the delta G, or for any pair of reaction, if the delta G for the pair of reaction is greater than 0, it is not a spontaneous reaction. Therefore, there will not be any corrosion. You can be assured that that material, that metal, is immune to corrosion. As opposed to this, if you take a pair of reaction, one of which is an oxidation of a metal, if delta G is negative for that pair of reaction, corrosion may be possible. So why do I say may be possible? Even if delta G is negative, in some metals, the formation of a metal oxide film can passivate and suppress further corrosion. Okay, so if delta G is negative, you cannot be assured that there will be corrosion. The corrosion might be possible, or passivation might be possible. So this way of visualizing a corrosion cell using two different electrodes and thinking through the delta G of a pair of reaction, one of which is anodic reaction, another is a cathodic reaction, gives us an indicator whether corrosion is possible. In the next lecture, we will take up a very important topic, which is central to corrosion. We will discuss Fourier diagram in the context of corrosion reaction. Thank you.